right. So today I'm going to first of all very quickly talk about what we have been talking about last time. Like very quickly, just like kind of scroll through all the things that we wrote, and then afterwards we'll continue with like the rank generating function and see some interesting thing about that. All right. So let's see. Um, so so we talk about the partial order set. We have all these examples that we talk about, like Boolean algebra and like the DN, the divisibility poset. We talk about like the subpartition poset, the pattern poset, the Young lattice, and also like this is the one that relates to the subspaces. So we do have a bunch of examples. We drew out all these like Hasse diagram, and you can see that like they in this case that I showed you before, they are all graded, meaning that you can easily tell me like which level these vertices, meaning that these elements are living in. So that's like visually very easy to rank them. And then the rank, we actually have a better definition, is telling you like you can talk about the length of the chain. So I'm going to really quickly get through that. But these are the examples that we have. And then we also talk about order preserving map and order preserving bijection, so that you can say two things are exactly the same. And we also talk about dual. Dual is just basically flipping your relation. So your hazard diagram would be actually upside down. And then if you flip it and then still the same, hazard diagram is exactly the same here, then we call it like a self-dual. And just to kind of remind everybody here is that like all the hazard diagram, they, even though I draw it like this, they are actually direct the graph going up. So this is a very important thing, because when we flip, these these are actually still like the graph we are going up. So we are trying to see like when we look at these two graphs, are they the same thing? And so because of that, like you can see that these two guys are actually not the same, because one is like this, and the other one is like this. So even though you know that like, oh, as a graph, if it is like not a direct graph, then they are the same graph. But like in Poset Hasse diagram is actually secretly a direct graph. We just didn't write out. Everything go up because we have an order. Everything above like this, that you have a line, and then the one higher is going to be like the one in like the larger one when you compare two things. So two things that links by a path is comparable, and the two things that are not linked by a path is not comparable. So we call it like incomparable. And so like we also like just draw out all the possible Hasse diagram up to 4 vertices. And then we talk about the notion of subposet. And then there are basically two main versions. One is weak and the other one is strong, which is the induced one. And then a special weak subposet is the refinement. And for most of the part that we are going to talk about, we always talk about, like when I say subposet without saying it's the weak subposet, then I'm actually talking about the induced version.
Just
So,
quickly interrupting, Anna. Are your slides supposed to move? Nothing's moved.
oh, nothing is moving. Okay, let me do it again. Do you see it again here? Does it move?
Yeah, now it's moving.
Okay. But the previous things are okay, right? All right. So let's see. All right. So here, so we are talking about the subposet. We talk about the induced subposet. Basically, it's just the induced graph. And then afterwards, we use that idea to talk about a very special induced subposet called the interval. Interval, you give me 2 points that are comparable in your element, and then they will form an interval. And so, like, for example, in the D90, you will see that like 90 and the 5 are like comparable. And so if you find the interval is everything that are comparable between them. So therefore you have like these subposet. And then afterwards, we talk about minimal element, minimal and maximal element, minimum and maximum element. They are different. Maximal element is just saying that nothing can be compared above. Minimal elements are saying that nothing can be compared below. Maximum element is the element that can compare to every single thing in the poset. And it's the top one, so everyone is smaller than it. And minimal element is everything is bigger than it. So you can compare to everybody and you are the smallest one. So here is a very good example, very simple. You see that the one in blue is the maximum element because nothing is above these three dots. But there's no that's no maximum element. So they are all maximal element. So a maximum element meaning that do you find any dot here that can compare to everyone? And also is the highest? No, right? Because nothing can compare with this guy, and this guy cannot compare with other thing. So same idea, minimal element. So these three dots here are minimal element, but they are not minimum because minimum has to be unique and also it has to be compared to everybody. These three dots cannot compare with each other, so that's already saying that they are not minimum element, but they are minimal element because there's nothing below them. And then if you're maximum and minimum, you're unique, so we give you a name. So usually we use these two notation, and 1 and a 0 with a head to denote the maximum and minimum element. And as you see, not every Hasse diagram would have maximum and minimum element. All right, so and then we also talk about something called like locally finite, just saying that like if all the intervals that you look at, they are all finite, then even if you are an infinite poset, you are still a locally finite poset. So for example, like these two are the examples of infinite poset that we have before, but they are actually locally finite because when you take any two elements and then look at the like the subgraph, basically the subposet, they are actually finite subposet no matter which two elements that you choose. So therefore, even though they are infinite poset, they are actually locally finite. We also mentioned the notion of convex subposet there, but so and then we talk about chain. So a chain is just a totally ordered subposet. And so what it means is that you take the points inside your poset, and if you can compare any two of them, then that's form a chain. So for example, in D90, you can see this 4 dots. Like you can draw a path to go there, and it's a single path. So that means any two elements among these 4, you can easily just compare them. However, this is not like saturated because you can actually make it bigger. So you can just squeeze in a 5 and still make it one single path. So a chain doesn't mean that they have to be consecutive elements on your route, but as long as they are in one single route. But they are not saturated. So saturated means that from the start to finish, you have to include every single location. You don't jump stop. So you can think about this as like a bus route. And then if it is like stopping in every single stop in your path, then it's guaranteed to be saturated. And if you just like express line that you just like skip some of the stops, then it's still a chain. It's still one route, but it is not saturated. And then maximal means that like this path, you cannot make it longer at all. Like that's the longest path that you can take. So if you are maximal, meaning that you cannot make it any longer, so therefore it must be saturated. But saturated doesn't mean that it is maximal. So you can think about like this is like a saturated chain, right? Because like you from the start to finish, you actually include every single bus stop if you think about it like that. But you can actually take a longer bus ride from like below 1 up to that includes this part. So then therefore you can actually make it longer by getting things like outside your start to finish, and then that means that you are not maximal even though you are still saturated. So we talk about in a locally finite poset, like a chain must look like this. So you always have, if you have a chain, then you have like a covering relation. So like a saturated chain has to be created by covering relation, meaning that like if you are a locally finite poset, then if I want to look at a chain whether it's saturated or not, I just need to like draw all these dots and then look at all these like a path from one to the other ones. Because it's a chain, so you have a path to go there, and then you just make sure that the path, every single thing here is an edge on your Hasse diagram. So for example, here, when I do this, I realize that, hey, from 1 to 10, this path is not a single edge. So that's not a covering relation here, meaning that it's not saturated. So that's how you can test by like visually looking at your Hasse diagram. And then we talk about the length of a chain, which is the number of elements on your path, and then -1. So basically the number of edges that you have inside your chain. So like edges in the sense like this kind of one edge. So if so basically what the length is just the number of elements -1, or you can think about the number of stop that you would go ignoring your starting stop, and then just like think about how many stop your bus will stop until your final location. So we also then talk about the rank, which is going to very directly related to what we are going to talk about today. So the rank of a poset. So give me a poset, any poset. I'm going to define the rank of a poset by looking at all the chains and then finding the length of a maximal chain. So basically thinking about the longest chain that you have inside your poset, and then that becomes your rank. If every maximal chain is going to have the same length, then you call, so of course your rank would be n. And also we can define a unique rank function that tells you like each element, whether it's rank 0, rank 1, rank 2, and so on. And the way that you define it is that if you're minimal, then you have rank 0, and then afterward you just work your way up, and then you will know each rank. So so this is the rank of a poset. And by Rabelais notation, we also say a rank of an element. It's just basically your function rank function value. So we did all this example. So you can see that like all these guys here, you can see the rank, like the rank of these elements. So for example, this is rank 0. These all these guys are rank 0. And then if you have something like this, you have rank 0, rank 1, rank 0, rank 1. This one is not graded, so I cannot have a rank function. But anyway, so if you don't see this dot, then this one is rank 0, rank 1. But with this dot here, the problem is this is not graded because like you have two maximal chain, and then this maximal chain has length 1. This maximal chain has length 0. So not all the maximal chain has the same length. So therefore, you cannot even define the rank of elements because you cannot find a rank function. But the rank of the poset is just the biggest, like the longest chain size. So here, therefore, you still have the rank of the poset. You just don't have the rank of every single element. So that's like, even though when I say rank, you have to be careful to think about whether it's a rank of a poset or rank of an element. Anyway, so last time we did all the examples here up to like the number of elements is 4, and then we try to look at whether something is graded or not, and then afterwards we don't have time. We run out of time. but we define the rank generating function. So today I'm going to study the rank generating function of all these examples if you actually are graded. So you can only do it graded because I have to say like the rank of an elements of rank I. So if you are graded, you will have a rank generating function. And I'm going to do that for all these things if they are ranked. And then also all these examples beforehand. So like these examples that we have, we are going to study the rank generating function. All right, so let's get started here. So basically I can only do the things these which are graded. Like if it is not graded, I cannot do it. And so let's see. So for example, here, this is 0. So meaning that like there are one thing with rank 0. So your rank generating is function is just 1 times t0. So it's just 1. And this is you have two things with rank 0. So therefore your rank generating function is 2 times t to the power 0, which is 2. Here you have 1 with 0 rank, 1 with 1 rank. So your rank generating is 1 plus t. Here you have 3 things with rank 0. So 3 times t to the power 0. So rank generating function is 3. This is the second one here. It's not graded, so I cannot even define the rank generating function. And next one is graded, so I can define it. So I have 2 things with rank 0 and 1 thing with rank 1. So that will be 2 plus t. Here, the next one here, you have 1 thing with rank 0, 2 things with rank 1. So you have 1 plus 2t. And the last one, you have 1 thing with rank 0, 1 thing with rank 1, 1 thing with rank 2. So you have 1 plus t squared. Okay, so let's do the p equals 4. Here you have 4 things with rank 0, so you have 4 here, and then all these 3s are not graded, so these 4 are not graded, so I cannot do it. And then now let's see these guys. Here I have 2 with rank 0 and 2 with rank 1, so I have 2 plus 2t. Here is the same. You have 2 with rank 0 and then 2 with rank 1. So again, 2 plus 2t. And then same thing here, 2 plus 2t. This is a little bit different here. You have 3 things with rank 0 and 1 thing with rank 1. So is 1 thing with rank 1. So you have 3 plus t. Here you have 1 thing with rank 0, 3 things with rank 1, so you have 1 plus 3t. So now, like after you do it several times, you will always like understand that this is the constant term, this is the coefficient of your t power and so on. So for example, here you can see that there are 2 things in the constant term, so 2 plus t, because you have 1t and 1t squared. So you have 2 plus t squared. This is 1 plus t plus 2t squared. 1 plus t plus 2t squared. And then you can easily understand the relation between the dual because you're basically flipping the coefficient here. And then the next 2 are not graded, and only these 2 are graded, the last 2. So here you can see 1 plus 2t plus t squared. So 1 plus 2t plus t squared. The other one is 1 plus t squared plus t cubed. Right. So that's how you find the rank generating function. All right. And so now, like, okay, well, if you give me a Hasse diagram and if it is graded, I can actually visually tell you whether it is, oh, sorry. Is it the, okay. So you can visually tell me whether it is, like the rank generating function, what that is. But what if I cannot always draw it out, right? Like when the Hasse diagram is big enough, then I may have trouble. So what I'm going to do is to give you like some non-generating function of the examples that we have before. So let me just write a table here. So let's look at the poset P. Let's draw this out. Okay, and then the rank of it, the rank of any element P. Okay, and then we are going to also look at the rank of P. And then we are going to have some space for the rank generating function. Okay, so let's start with our very beginning example, which is the basically the chain. So if you have 1 up to n using the normal like comparison rule, then you can compare any two numbers from 1 to n, right? 1 to up to n. So that's the Hasse diagram. And so if I ask you like what is the, if I have an x within 1 to n, I want to know the rank of x. Of course, that would be just rank of x minus 1. So the rank of p is n minus 1. And then so the rank generating function, so the 1 here is rank 0, and the 2 here is rank 1, and the n here is rank n minus 1. And each rank you have exactly 1 dot. So you have this rank generating function, which is like 1 plus t squared plus dot plus t to the power n minus 1. And this is actually something called a q number if you replace the t by q. But anyway, so usually people write it like this. Or why do we use n? Because there are n things here. Or another way to look at it is 1 minus t to the power n divided by 1 minus t. Okay, so that is the rank generating function of a strict line like this of a chain. So any chain would have this type of generation function. All right, so how about the Boolean algebra? Right, so we call the Boolean algebra is something like, oh, I have like some empty set, and then maybe you have like 1 and 2, and then you have the subset. So this is like, say, for example, I have the Boolean algebra 1, 2. Then this is the Hasse diagram. This is B2. And then the Boolean algebra of B3 here is just like the subset of 1, 2, 3. So therefore, that's the one. Sorry, I have to scroll so that you can see it. So this is the one, right? You have subset 1, 2, 3, 1, 2, 1, 3, 2, 3, and 1, 2, 3. So that's the Hasse diagram. And then you can see that it's like 1, 3, 3, 1. Right. So how do you find the generating function? So see, this is 1, 3, 3, 1. The other one here is 1, 2, 1. So you kind of see that that's the binomial. And is it always true? And the answer is yes. Because if you, first of all, think about like if you give me an element inside the B, like Bn, and then so if I want to know which rank that it lives in, then it's just really basically the number of elements that it contains. So for example, here you can see that if you have nothing, you are rank 0. If you have exactly one thing, you have rank 1. If you have two things, you're rank 2, and so on and so forth. So the rank of an element inside P is basically the size of the element. So the element is a set, so this makes sense, the cardinality. The rank of P is just like the top part. So that would be your n minus 1. N thing. So you have, because here you're rank 2 because you have 2 elements, and then if you have like 3 things, then your rank is 3, and so on. Okay, so now how do I know how many elements are in each level? So I know that that's an empty set, right? if say, for example, you are in Bn, meaning that you are like 1, 2, up to n. So then I want to know how many subset that has one element. So of course there are n of them, right? So t to the power 1. How many subset has exactly 2 elements? So that's actually n choose 2, t squared. And then how many elements have 3 things? So n choose 3, t 3, and so on and so forth until you hit n and tn. So therefore, this is the rank generating function here. So let's record it here. So 1 plus n choose 1t, n choose 2t squared up to n choose n, tn. So of course, this is just 1 plus t to the power n. So that gives you the Boolean algebra. Okay, so we have the generating function of these two. The next one that I want to talk about is the divisibility one. So the dn. Okay, and so if I give you an element, so let's just go back and then look at one example. So let's say, for example, we look at the D90 here. Okay, let me just copy and paste it here. So the D90 here, and I want to know like, okay, well, just randomly choose a number, say, so for example, 30. How do I know what is this rank? In here, we realize that like, okay, well, the path that I go here, any path, is always have 1, 2, 3 edges. So I know that it should be of rank 3. But how do I know that it's 3? Well, think about each edge, what it's going to give you. Remember, each edge is actually a prime. So 1 to 5 is multiplied by 5, multiplied by 2, and multiplied by 3. So these are actually your prime factor. So basically, you're thinking about how many prime factors that you have to get to 30. So for example, 18. 18, if you write out the prime factorization, is 2 times 3 times 3. So that is 2 times 3 times 3. So you can see that like each path corresponds to a prime number. So, and also the rank, if you're ranked it, the rank of an element is the number of edges to go from below and go up. So therefore, the rank of an element X here is just the number of prime factors, of course, including multiplicity. Of X. All right. And so what is the rank of the whole poset? Well, the same idea. So that's the same as asking what is the rank of this guy, which is again the prime number of n. So basically the same thing as we have here, but change the x to n. Okay, so how are we going to find the rank generating function? So the rank generating function is just, so first of all, let me write out the answer and then I explain why that's true. So the answer is 1 plus t squared plus da 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 plus t to the power a1 up to 1 plus t plus da da plus t to the power ak. And what are these a1 up to ak here? So here n is written out as the prime factorization like this. Okay, so that's the unique prime factorization of n. Okay, so how come the rank generating function is like this? Well, because think about what is the rank generating function. The rank generating function is saying one, like how many number with, so the rank generating function of this is always 1 plus something, because you always have the factor 1 here. And then afterwards here is the number of prime that you get, right? So so this is like number of primes factor, like actually the prime in n. That's without multiplicity. In this case, it's k. to the power t to the power 1. And then you have something t to the power 2 and so on. So these guys, when you count, they are counting the factors of 90, right? Like, so these three guys are the factors of 90. These three guys are the factors of 90, but like of rank 2. Why is that? Because they are going to be created by two of the elements. So let's just really do this using the D90. Maybe that's easier to understand. So what I claim here is that the D90, the rank generating function is like this. So you look at 90. 90 is 2 to the power 1 times 3 to the power 2 times 5 to the power 1. So I'm claiming that the rank generating function is 1 plus t. So because this is 1, and then 1 plus t squared times 1 plus t. And then I'm going, like, when you multiply these guys, right? Then you will get something like 1 plus something t plus something t squared plus da da da. Well, how do you get the t? Well, the t are the ways that you multiply these parentheses. So for example, you can create a t by 1 times t here, or t times 1, like 1 times t times 1, t times 1 times 1, or you can also have 1 times 1 times t. And then so there are 3 different ways to create them. And how am I going to correspond to these 3 numbers, 2, 3, and 5? Well, just think about these. This is the 2. This is the two parentheses. This is the 3 parentheses, and this is the 2 parentheses. And 1 means that it corresponds to 2 to the power 0. This corresponds to 2 to the power 1. Same thing, this is 3 to the power 0. This corresponds to 3 to the power 1, 3 to the power 2. This is 5 to the power 0 and 5 to the power 1. So when I do 1 times 1 times 1, 1 times 1 times t, then I'm actually correspond to choosing 2 to the power 0, 3 to the power 0, and 5 to the power 1. That is actually just 5. So that corresponds to 5. And so like the 3 different ways that I create the t is basically the 3 different ways that I create the 0, 0, and 1 in the power. So therefore that corresponds to a single prime. Let's look at another element here to make it clear. Remember we talked about 30, right? So the 30 here is basically so 30 is 2 times 3 times 5. And it says when you look at the rank generating function, in this case it's like 1 plus 3t plus 4t squared plus 3t t plus t to the power 4. How do I know that? Is 1, there are 3 elements, 4 elements, 3 elements, 1 element. And so like the 30 is here, meaning that like it contribute to the one of the 3. So this 3 is counting 18, 30, and 45. So 30 is inside this 3, and it gives you 1, like a contribution 1 here. How am I going to see that? Well, it's the same as thinking about when you multiply this guy out, how am I going to get t cubed? So you can either get t cubed by this times this, which is the 2 to the power 1, 3 to the power 1, and 5 to the power 1. That's exactly our 30. Or you can make a t cubed by t squared times a t and then times 1. In this case, you are creating 5 to the power 1, 3 squared, and then 2 to the power 0. So that gives you 45. And that's this guy here, right? So you can see that like if you give me a number, I can easily tell you because, oh, it has 2 to the power 1, 3 to the power 1, 5 to the power 1. Then the way that I choose the t cube is fixed because that's the t to the power 1. And then 3 to the power 1 is just this guy, look at the same power, and then 5 to the power 1. If you're thinking about, oh, how am I going to get the 18, right? 18 is 2 times 3 squared times 5 to the power 0, meaning that you create the t cube by doing t and then t squared, and then 1. That's another way to get a t cube. So if you understand the generating function, how it works, then this should be easy to get. Anyway, so that's the rank generating function. You can also use this notation, this notation to talk about it. And so the notation that we use here would be just a1 plus 1 t, a2 plus 1 t, up to ak plus 1 t. So in our particular case here, 90 is this guy, so your power is 1 to 1. And so the rank generating function, let me use the notation, f of d90 t would be 1 plus 1 is 2. So 2t times 2 plus 1 is 3, 3t times 3t. So that corresponds to 1 plus t, 1 plus t squared, and 1 plus t. So that's the rank generating function of dn. All right. So things start to get more and more interesting when we look at more complicated examples. So let's look at another example. So the other example that we have is the pi n, which is the set partition of the set 1 to n. And just give you the Hasse diagram. Let me just find it here. Okay, so let's do this. Copy. Go back here and paste. So this is like our pi 4. You are having a subpartition of 1, 2, 3, 4. And so if I want to know like what is the rank of an element, like how do I know? Well, like if you have everything, like you have 4 subset, like if you have 4 partitions here, you're rank 0. If you have 3 partitions, you're rank 1. 2 partitions, you're rank 2. And then you have 1 partition here, the 1 block, then you're like the highest rank, so you're rank 3. So think about it, it's like you have 4 blocks, then your rank is 0. 3 blocks, your rank is 1. 2 blocks, your rank is 2. And then 1 block, that's the highest one, your rank is 3. So when you add them up, they're always 4. So meaning that the rank is the 4 minus the number of blocks, right? Because number of blocks plus your rank is always 4. So you have this. And what is this 4? Well, the 4 is this 4. That's the n. So in general, your n, like your rank, is n minus the number of blocks inside X. And I'm just going to write the size of X. It's the same as the number of blocks. And then the rank of P, well, it's the highest element. The higher element has 1 block, so that will be n minus 1. So why do I have the rank of P? Because the rank of P in these cases, they are all the degree of your generating function, of the rank generating function. So for example, here you can see that it's degree n minus 1. This guy is degree n. And this guy is the degree, like, is the number of prime factors of n, including multiplicity. Here, you are going to expect a polynomial with rank n minus 1. Okay, and then so the answer here is, that's nothing fancy here. I'm just going to write it out using the notation that you count set partition. So this is from I equals to 0 to n minus 1 because that's the possible ranks. And then how many things are there? There are, and choose the size of the thing inside rank I. So the thing says in rank I is like this, t to the power I. Okay, so what is this s here? This s and r is the number of subpartitions of n into our blocks. And it has a name. This is called the starting number of the stack second kind. So you see that as a second kind. Of course, that's a first kind, and the first the first kind is actually related to something related to cycles in a partition in a permutation. But I'm not going to talk too much about that one. If you're interested, you can put the name starting number of the second kind and then like look at the OEIS, then you can see a bunch of interesting formulas. So I'm just going to leave the generating functions like this for this particular case and then move on to other ones. So let's see. And so the next three of them are actually quite interesting. Okay, so the next one that we have on the list is BNQ. Okay, so remember, this is the poset that is the subspace of FQN. Again, let me just pull out the previous example so that you can see it. So this one, copy. Okay. So this is one of the example, which is like look at F32 and then look at all the subspaces of F32. This is the Hasse diagram. In this very particular case, we have 1 plus 4t plus t squared. Okay. But in general, how do you find it? Well, first of all, like, okay, if you have an element inside B and Q, how do I know that your rank? Well, your rank is basically your dimension, right? Like the dimension 0, dimension 1, dimension 2. So that's the dimension of your subspace. So it's dimension X. And of course, like when you're up to the top one, it's just the dimension N, and the N is right here. So that's dimension N. And so you're going to have a generating function, rank generating function of degree N. Okay, so now the question is like, okay, well, I know that it must be t to the power I from 0 to n. So basically it's like number of subspace with dimension I. And the answer here is n choose I but q. Okay, so let me just explain what this is. So n choose I q is just n q factorial divided by I q factorial and then n minus I q factorial. So when q is, so this is very similar to your n choose r, right? N factorial, r factorial, n minus r factorial. That's called a q analog of your binomial here. And okay, so what is this like? NQ and n factorial. What is that? Well, it's just NQ factorial. It's just NQ times n minus 1Q times up to 1Q. And then what are all these like Q thing? That's exactly the same as the T that we have here. So basically, this, if you really write it out, the first one is 1 plus t squared plus plus t to the power n minus 1. 1 plus t squared plus plus t to the power n minus 2 up to 1 plus like 1 plus t up to t to the power 1. So like 1 is just 1 here. Notice that if you, oh, sorry, I should write everything in Q. Q, 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 Q. Just change your variables. Notice that if I put Q back to 1, so if you put Q equals to 1 here, this gives you N. This gives you N minus 1, and then that gives you 1. So basically, if like NQ is just equals to N if Q is 1. If I define NQ in the way 1 plus Q up to Q to the power N minus 1. Okay, so that's the Q number. And it's called Q number because it's a generalization of our usual number when you plug in like Q goes to 1. And then, so the factorial is just basically the same idea here. And now the question is, how come the number of subspace with dimension I in FQN is actually this one? So this is actually, I covered it in my course in GC. But let me just very quickly tell you why. Let me actually just give you the notes. I think it's this one. Okay. So this is an easy proof here. So any k-dimensional subspace of FQN is actually n choose k. So the k-dimensional here, n is this n, and a Q version. And why is that? Well, there are two ways to count. You can either, first of all, just count how, like to form a basis, right? To form a basis of k linearly independent, like you find k linearly independent vectors in FQN. And to form a basis, you have to be ordered. So first of all, you find any vector that you like. So you have q to the power n minus 1 choices. Once you find that, then the next one that you can choose would be n to the power n minus q, because there are exactly q minus one thing that is parallel to what you chose before when you were in FQ. So and then afterwards you have like minus q squared minus q cubed and so on, and then you realize that, oh, this is the number of ways that you can find a k-dimensional ordered sets of k linearly independent vectors. So that's one way that you can create a basis. Another way to create a basis is, first of all, you choose a k-dimensional subspace and then find a basis inside, right? So first of all, I don't know how many ways, but this is what I have. You choose you fix a k-dimensional subspace, and then once you have the subspace, then you form a basis. So the basis would be q to the power k minus 1, so any vector inside your subspace that you pick. And then the next one, you have to be linearly independent. And so you have q to the power k minus q choices, and so on and so forth, until you find the last one, right? So basically q to the power k minus q to the power k minus 1. So this is a way to form a basis in a k-dimensional subspace, and this comes every single way that you do it. We also have the other way. So therefore, if I want to find the number of k-dimensional subspace, that would be just this divided by this. And so now you just do some simple algebra, you'll realize that back to and choose KQ. So that's like a easy fact that you can prove combinatorially by just counting in two ways. So let's go back to our examples. Let's see which one. Okay, so that's why we have this notation here. All right, and let's see. We have another one, which is really my favorite of the day. It's the S. What is the S? Let me again go back and give you the example. Remember, this is actually just the pattern poster that we have. So these are the two guys that I'm going to talk about. Copy. Okay, so go back here. All right, so this is the one that I'm going to talk about. And this is actually very easy to count because like for each of the elements inside, right? What is the rank? Well, if you have nothing, you're rank 0. You have one thing, you're rank 1. You have two numbers, you're rank 2. Three numbers, you're rank 3. So basically, it's the size of your thing. So it's just the size of thing. What is the rank? Well, it's an infinite poset, so it's infinite. So what does that mean? That you're going to get an infinite series instead of like a polynomial with a fixed degree. So like you don't have a degree. All right, so what is this generating function? How do you count? Well, that's actually super easy. This is 1, 1 times t0, so 1 plus t plus t, 2t squared plus 6t cubed, right? So this is like 1 plus t plus 2t squared plus 6t cubed. The next one would be the number of permutation in like 4 elements. So that would be 4 factorial. So 24t to the power 4, and so on and so forth. The next one, 120t to the power 5, right? And then if you write it in summation form, it's actually like I from 0 to infinity. N, let me use n. And from 0 to infinity, n factorial times t to the power n. Okay, well, that's just that. And yes, that's the answer. But that's not the like that's nothing interesting here. It's just like n factorial t to the power n. But why I said that's interesting is because the way that you can write it. So first of all, let me give you the surprising fact. At least I found it surprising. Is that this guy you can write it in a continued fraction. So this has a interesting fact about it. I think. Hopefully I spell it right. I don't know how to pronounce it, but that's the name of the continued fraction. Okay, so what does that look like? So it says that n factorial, I use t, but like let me use x here. It's the same. Just like look a little bit better. Well, let me use t. Okay, so how do you write it? It's actually 1 over, okay, so 1 minus, and then t over 1 minus t over 1 minus 2t over 1 minus 2t over 1 minus 3t over 1 minus 3t over 1 minus 4t over something 1 minus 4t over 1 minus 5t over da 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 da. You just continue this pattern, and this pattern is so nice, right? It's 1 minus like t, 2t, 2t, 3t, 3t, 4t, 4t, 5t, 5t, and so on. And the way that like how did somebody prove something like that? Well, that thanks to some interesting facts about factorial. So n factorial can be written in if you do calculus, you'll see that that's just x to the power n e to the power minus x dx. All right. So now if you use this fact, then n from 0 to infinity n factorial t to the power n is just summation 0 to infinity. And then you just replace, so now I will have x to the power n e to the power minus x times tn, and then, summation, right? Like I'm just having, let me just do this like this. So summation n equals to 0 to infinity. You have n factorial, which I'm going to replace by the integral times t to the power n, right? And then now I can pull out the integral because there's basically limit of summation. And so I can just swap, and then xn e minus x, and then tn, and then dn, dx. And then now you can see the EX is just a factor that you can pull out. So I'm going to pull this out. So I'm going to rearrange, and I have this guy here. Okay, but this is like a geometric series because this is basically xt to the power n, right? So so the xt to the power, oops, the xt to the power n here, we know how to write it, because it's just 1 over 1 minus xt dx. So 0 infinity e to the power minus ex 1 minus xt dx. And this one converges for x equals for x less than 0. It does not converge all the time. converges for x is less than 0. And then like there are some theorems to tell you how to write some form like these guys to continue the fraction, and like this is the setup of like to use the theorem. But anyway, so there's a lot of like very nice formula to write all these like numbers. Like you can view n factorial instead of just 1 times 2 times 3 up to times n. You realize that that's a answer of a nice integral. And also you can just put it in here, do some math, and then you have a very nice integral of this guy, right? And also you can write it in this way. Now this is not the only way. Because there's another way that actually writes another continued fraction, and it actually converts faster. And this guy is called the Jacobi continued fraction. So what is that? Well, instead of one, like just 1 minus t, 2t, 2t, 3t, 3t, and so on, it's just a little bit more complicated, but the pattern is also very nice. So it's just going to be like this. So it's just 1 minus x minus, and then x squared over 1 minus 3x minus 4x squared, 1 minus 5x. So all these guys be 1, 3, 5, so odd number. And then minus 9x squared. So this is basically, if you like, you can, instead of writing, like you can see that this is just 1, 4, 9. And the next one is easy to know, 1 minus 7x minus 16x squared, and so on and so forth. So this actually converts faster. And is like, you can see that that's actually really nice. Like, just look at this simple way, and then you can write in terms of like very nice patterned continued fraction that is actually very beautiful when I first see it. So I really want to share with you guys. All right, so now we only have one more to talk about, which is our Young lattice. Okay, so Young lattice has a lot of like very interesting property, but for now we are just going to look at the rank generating function. So in this case here, like you can see that, oh, that's 1 plus t, that's 2t squared, there are 3 things, so 3t cubed, there are 5 things, 5t to the power 5, and so on, right? What are these guys, right? What are these guys? Well, first of all, like if you like the rank of each of the elements are just the number of boxes, right? No box is rank 0, 1 box rank 1, 2 box rank 2, 3 box rank 3, 4 box rank 4, and so on. So now these are just asking like, oh, how many things with exactly say for example, this is how many things are with a certain amount of boxes. So the rank generating function would be something like something here, and then t to the power n, right? And from 0 to infinity. What is this? Well, the number of boxes are the same, and they are partitions, right? Remember, they're actually just partitions. So basically, it's asking you the number of partitions of n times t to the power n. Then that's actually the generating function, not the rank generating function, but just the rank generating it's just the generating function of the partition function Pn. So this is usually called Pn. And so this is well known. This is just 1 plus t squared plus t cubed plus da da da. 1 plus t squared t4 plus t6 plus t8 plus da 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 da. 1 plus t cubed, t6, t9, t12, plus dot dot, and so on. So you can write as 1 over 1 minus t, 1 minus t squared, 1 minus t cubed, and so on. Or a nicer way is 1 minus t to the power k, k is from 1 to infinity. Okay, so very briefly explain why this is true. This is very similar to the DM when we are explaining things. So for example, think about this 5t to the power 4. And the 5 is actually talking about these 5 things, right? This 5 partition of 4. And how do you get it? It's either 4, 3, 1, oops, 3, 1, 2, 2, 2, 1, 1, and 1, 1, 1, 1. So that's these guys. Okay, so think about okay, well, that means if I look at these things, there will be 5 ways to make t to the power 4, right? I can make t to the power 4 by just simply take t to the power 4 here times 1 everywhere. But what is this way correspond to here? Well, this is actually talking about, this is like how many ones that you use, how many twos that you use, how many threes that you use. So for example, t to the power 4 meaning that you have t, because everything is a multiple of 2. So this 4 is just saying that you have 2 times 2, meaning that you get, this is just 2 twos. So that corresponds to this one. Now, if you're saying, hey, what if I want to create 2, 1, 1? Well, 2, 1, 1 means that you use 1, 2. So that would be here. And then you use 2 ones. So you have 2 ones here. So this is the 1 bracket. This is the 2 brackets. So that's how you get the t to the power 4. And then all the other guys you don't take. So you multiply by t to the power 0, meaning that I have no 3s, no 4s, no 5s. Now if you're like, oh, what if I want to do 3, 1 then? Well, meaning that you have 1, 3 and 1, 1. So you're going to take this, you have 1, 1 and you have 1, 3. These two add up, and then all, like, you have no 0, and then everything takes the 1. So you have t to the power 4 in this way. So that's another way that you can get a t to the power 4. So you can see you have a bijection. If I say, for example, if I just randomly pick a term here, let me just erase everything here. If you randomly pick a term, say for example, t3, t8, t cubed, like this, and then everything else just 1. What is the partition that I'm looking at? Well, t, like you're going to create the term t to the power 3 times t to the power 8 times t to the power 3. So you're going to form a partition of size 3 plus 8 plus 3, so size 14. You're going to form t to the power 14. So it's a partition of 14. But what is that partition? Well, you have t to the power 3 in the one thing, meaning that you use 3 ones. And then you use t to the power 8 here, and they are all 2, so there are 4 2s. And you use up 1, 3. So meaning that this way to create, you correspond to 3, 2, 2, 2, 2, 1, 1, 1. And then if you, of course, if you add them up, that's the 8, that's the 3, that's the 3. You add them up, must be 14. So this is like the bijection from the term that you choose to the partition. Or if I give you a partition, you can easily tell me how to choose the term. So therefore, this gives you the generating function of the way to count partitions. And so that also is the same as your rank generating function. So to complete the table, this is y, this is the number of boxes in the partition. Again, this is infinite. And then your rank generating function is just very nice. K bigger than or equal to 1, 1 over 1, 2 to the power k. So that gives you all the rank generating functions of all the examples that we have discussed during all these lectures. But you can see that if you have any poset that you study, one thing, if they are ranked, you have to think about whether they are ranked. If you have a graded poset, finding the rank generating function is actually one thing that you can study. And the good thing about this is that sometimes you will see interesting property, just like the continuous diffraction that we just shared here. But hopefully if you encounter any graded poset, you will be at least first of all look at the rank generating function. So I'm going to stop here, and like if I have like next time if I come back to give like another set of lecture, I will continue with this series and then talk about more things about like the poset.
Thank you, Anna. This was the best explanation of rank generating function I've seen. I'll stop the recording and then we can chat.